Hello, flat earth researchers, debaters and debunkers. Many of the so-called proofs that we live on a globe are related to making observations of the sun. Of course, the assumed heliocentric model is that we have a gigantic sun and we are on a tiny earth that's rotating to give us night and day, and that the earth is orbiting the sun once a year. And in connection with that, we have the Gregorian calendar, and we are told to imagine this heliocentric model and are told that this is our reality because of the observations that we can make. Of course, we have experiments of old that are said to have proven irrefutably that we live on a spherical earth of a certain diameter or circumference simply by observing the shadows created by the sun, Eratosthenes. So of course we've got this idea that people who go against this idea or question this idea, i.e. flat earthers, are questioning 2,500 years of science that proves we live on a globe. But I'm going to just have a look at how it's impossible that we could have something like the Eratosthenes experiment showing us that we live on a globe, given the idea that the sun is massive and the earth is a tiny rock spinning around orbiting the sun. So I've just done this very simple illustration which when we compare this kind of view to reality, one thing that we can say is that it kind of makes sense. This is what you'll hear from a lot of people who have realized that we don't live on a globe, and they realize that the flat earth just makes sense based on our observational reality. But it's very difficult to kind of put that across somehow. Why does it make sense? And it's like anything that makes sense. There are all these little clues which add up that we can compare with reality and say, yeah, I see that the sun is something local. The earth doesn't have to be moving. The sun actually does rise and set because it's traveling in a circle above a stationary level earth. This just makes sense, regardless of the kind of logic you might appeal to based on the idea that, the earth is another body of mass in the solar system. So it's logical that the earth is a sphere, just like everything else that we see in the sky. And of course, it's very difficult to detach from that idea. If the idea that's been given to us since we were kids, solar systems, and you're on a rock and you're on a globe that's going around the sun. So let's just have a look at what we can actually see with a side-on view, an orthographic view of two people looking at the sun on a flat earth. Now, of course, what the globe or heliocentric model attempts to do is to give us an objective reality. That is to say, for example, that the sun is a particular height above the earth. Now, in an orthographic view, we can do this. We could say, right, okay, there's the earth, there's the sun, and it's, for the sake of argument, we'll say 100 miles away. But of course, this can become very arbitrary. We're told that the sun is 93 million miles away and much more massive. But we're going to see how that just does not work if you want to actually measure shadows or the angle to the sun on a flat earth or a globe earth. Having a much more massive sun simply doesn't work. But first, let's have a look at how it does make sense on a flat earth. Here we can see two people looking at the sun, and this person here who is relatively close to the sun has a short shadow. Okay, so this would be the angle at which they observe the sun. And over here we have another chap who's further away from the sun. The sun hasn't moved. The sun has stayed in its objective height from the Earth in this orthographic view. But the shadow for this person is naturally going to be longer because this ray of light here is coming down at this angle, so we get a more shallow angle and a longer shadow. And of course, anyone standing directly underneath the sun will not have a shadow. So this works perfectly on a flat Earth. We actually get shadows of differing lengths depending on how close to being directly under the sun you actually are. Now, of course, what happens is we also have this subjective reality. So I've just put a line here, a blue line here, a horizontal line to represent these people's eye level. Now, for each observer looking at the sun, they are going to measure an angle to the sun from their horizontal line of sight. And of course, in that person's eyes, the horizon or the surface will appear to rise up to that person's eye level. So all the angles of elevation that they calculate or measure from their particular position on the Earth in relation to the sun will be from their particular horizontal line of sight or their eye level. So that's where the horizon is for each and every one of us on this Earth. And so all our observations to celestial objects or luminaries are made from eye level, from the horizon. So essentially the surface for each individual observer isn't objectively here anymore where we can see it in this orthographic view. It is subjectively up from their own eye level. Yeah? So of course this, alright, you get the same angles from the eye level to the flat surface here and here, but this is a subjective reality for each of these people looking at the sun. And so of course the further away you get from the sun, the lower towards our horizon that sun will appear to be. So for this person here, who's closer to the sun will appear quite high in the sky above them. But for this person who's further away from the sun will actually appear closer to the horizon for that person, regardless of what the objective reality is when it comes to the actual height of the sun above the Earth, where it actually is. For each individual person, that sun is going to appear in a location that's different, a location relative to their eye level and their distance from the sun. Yeah? The further away you get, the closer the sun will appear to the horizon of that individual observer. Really simple stuff. So this kind of illustrates both an objective reality where we would have an assumed distance from the Earth to the sun that wouldn't change, but for the individual observer, of course, it does change in their eyes. But what we need to consider is that we're told the sun is many, many, many times larger than the Earth, and we are told that it is about 109 times larger. Basically, you could get 109 globe Earths across the diameter of the sun, so we are told. So let's have a look at that scenario here, where what we have is this idea in the model when it comes to sun angles to the sun and the shadows. We have basically what we would essentially have is a flat sun above us, giving us these parallel lines of sunlight. Yeah. So of course, then with the globe Earth model, you say, well, this person is looking up at this angle and this angle relative to the Earth's surface, and we got parallel lines of sunlight. But this doesn't fit our reality. It's been made to work for the model, because basically by giving us a curved surface and saying wherever you are on that curved surface, you're looking up at parallel lines of light, or we have parallel lines of light hitting the Earth because the sun's much larger than the Earth, and so we can then judge or calculate or measure the angles of elevation to the sun, or the shadows that are created by the sun at the angle relative to the sun for this person or that person on the globe. Let's just give you an example here of the shadow you see. So I've put these black lines in to represent shadow created by these parallel lines of sunlight from a much more massive sun coming onto a globe. But there's a problem here with this model that doesn't fit reality, because what's actually going to happen with such a massive sun casting all this light onto a globe Earth? We're not going to get any shadows. Why? Because I have a line here representing sunlight coming in from this side over here. Bearing in mind the idea is that the sun is much larger than the Earth, so the sunlight is going to come down past us, but it's also going to come down in this direction, and it would eliminate the shadow. You see, it would be impossible to say this light here, this ray of light is casting a shadow from this person, because actually this person will also have light shining on them from this direction, so you would not get a shadow. Yeah? So given the model, the heliocentric model, which has us on a small Earth compared to a large sun that's beaming down light that covers the entire Earth, or half an Earth, the half of the globe Earth facing the sun, it still means that it would be impossible for anyone or anything to cast a shadow on the Earth, because you would always have light coming in from other directions, eliminating the shadow. It's simple. When you compare the ideas in the model, these compartmentalized ideas or so-called proofs or illustrations, with reality, we know that if we are on a stage and there is a light over here and a light over here beaming down on us, basically the equivalent to having a massive sun above us, we would not have a shadow either side, or the shadows would be faded or out of focus, or we'd get lots of different shadows. Yeah, but the fact is that when we're on the Earth, we get very, very sharp, distinct shadows, and that's only possible in a situation like this. Yeah, where we have a sun that, okay, has an objective position above the Earth, and it really doesn't matter how far away it is, but what happens is that we get shadows, and this is only possible on a flat Earth with a local sun. Yeah, it simply works. Now, often people will argue that if you add 3 or 4 or 5 positions with different people looking up at the sun, you will get different angles. They don't necessarily meet. Well, again, there are two factors there, because first of all, we have the individual subjective perspective of each observer. Again, there will be an apparent difference in the height of the sun above the surface for the individual observer, but also to what part of the sun are you measuring? Are you measuring to the center of the sun? And how big or small is that sun? If, for example, we made, let's just try right now and make a large sun, okay, on a new layer, all right, and make it yellow, and let's just make it, all right, like that. We'll fill it in with some yellow, okay, boom. So here we have a large sun. Again, it can be any distance or any height. It really doesn't matter. What's important here is that at what point for any observer do you figure that they are looking at this, or their line of sight is meeting the sun? Is it here? Is it here? Going towards the center? Is it down here? And how large or small does that sun appear for the observer? Of course, we are told that the sun is much more massive, but 400 times further away from us than, say, the moon. I can't remember if those are the exact figures, but basically the idea is that the sun looks small because it's so far away. But when you try to model this or illustrate this, you can, of course, you can model it any way you like. It's arbitrary. The distance and the size to the sun, you just try and make it fit to the presupposition that we're on a globe. But ultimately, you have to come back to making those comparisons with real life. That if the sun is larger than the Earth, globe or otherwise, we simply wouldn't have shadows on the Earth. It doesn't matter where you are on the Earth, you wouldn't have shadows. Now, of course, we know that we do have shadows throughout the day. It doesn't matter whether you're on the equator or way up north or south. The shadow, our length of shadow changes throughout the day. So it's this simple observation of our reality that tells us that the light source is local or smaller, and we are stationary, and the light source is moving above us to create those moving shadows. Because in this scenario, it doesn't matter if you're on a globe that's moving. Once you're facing the sun, there will be no shadows. It's either light or dark. There would be no shadows. So the only way we can actually observe shadows on the Earth is with this kind of scenario. A large sun or a small sun, height above the Earth, irrelevant, doesn't matter. The fact of the matter is that it makes a lot more common sense, and it's demonstrably so when you make an illustration and in real life, that we have a sun that is somewhere above a flat Earth. It's moving about, creating shadows of different length throughout the day, depending on your location. So, of course, if you're never near the equator, if you're always north of the equator, then you're never going to have no shadow. You'll always have a shadow. Now, the length of the shadow will depend on how far away the sun has gotten from you. Yeah? So that will then change the length of the shadow. And again, I encourage people to just try this for themselves. Go and make your own little models. Get a flat surface, get a curved surface, move the light about, move the surface about, and you will see for yourself what this actually means. If you try to model what we are told is our reality when we are given this heliocentric model, a massive light source beaming down on us on this small body, it's simple. You'd never get a shadow. All right? So anyone who brings up Eratosthenes or even sticks and shadows as some kind of observational proof that we live on a globe, they have no grasp on reality. All they can ever do is argue from the point of a model. But even so, as we've seen, that model and the assumptions made for that model have no basis in reality. Thank you very much.